Hi, in this tutorial I'm going to demonstrate some practical vertical um, dipole antenna. So first of all, um, I want to just give a brief um, introduction to the dipole. A dipole over a ground plane. So where we have a dipole right here, and I have like a ground plane, we'll have an image that'll have the same current directed to that. So that will form an array of two dipoles. One will be the actual dipole, and the mirror beneath that ground plane will form an array of two dipoles. The derivation of for the pattern, it's will be based on the E theta, and this will be the array factor. I'll describe that in more details on the next class, but just to mention that this is it's an array of two dipoles. So this is the E field. Okay, so the most important thing that I wanna point out here is that whenever you have a dipole, a vertical dipole, and you'll place it above a ground plane, a perfect ground plane, you'll start forming some of what is called scalloping. In this case, we'll be raising the dipole above the ground plane, and we'll start seeing the changes on the radiation pattern according to the height of the dipole above the ground plane. So the formula for that, it's 2h divided by lambda plus 1 will be the number of lobes that you'll form depending on how high you raise the dipole. Just a simple geometry to demonstrate some of the concepts. So we'll consider an infinitesimal dipole to be lambda around equal to lambda, the length of the dipole be lambda divided by 50. So that's the length of our dipole to be considered an infinitesimal dipole. If you're familiar with EasyNet, so the main things that I wanted to mention here is that the geometry will be described by the wires on the design. So in this case, I have that N1 and N2 being the bottom end of the dipole to be located at 0, 0, and 2 on the z-axis, and at the other end of the dipole will be at 0, 0, 2 plus lambda over 50, which is 0.02. Just another thing to mention here is that the units are in wavelengths, and the plot type, I'm going to be looking at that phi equals to 90, and the elevation plane is going to go from 0 to 180. Okay, so once I do that, by the way, I'm going to be sending you the model so you can try different type of heights by yourself. So this is what I'm going to get. As mentioned before, in this plot here, okay, so in this case, we're gonna do for two cases that they're demonstrated on the book. So for the case of the height to be 2 lambda, then I have the number of lobes that I'm gonna have in my radiation plot is going to be equal to 5. So if you start counting here, like half of the, if you're just looking at half of the plane, which be 1, 2, 3, 4, and 5 lobes, and the other ones will be a mirror around the azimuthal plane. For the case of like raising the dipole to 5 lambda, I'm gonna get 11 side lobes or lobes. If you count them, you'll be having that. Another thing to mention here, okay, so you could see the same results for both of these cases in figure 4.60 from the book. So in the case of like these solid lines, each half of it is gonna be for 2 lambda, and the other one is gonna be for 5 lambda. So there's like those two plots are being plotted in one on one plot. Okay, so in summary, to get the radiation resistance of a vertical dipole, we'll use this equation right here. For the directivity, it's gonna be determined by this equation. For the radiation pattern, we'll use this equation right here. Okay, so in the case for the radiation resistance and the directivity, we have a figure on the book will tells you like how the radiation resistance using those previous equations being plotted over height of from 0 to 5 lambda, and we could see values for the cases of that we demonstrated. So this is the plot. Okay, for example, like a height equal to 0, the directivity is gonna be about 4.77 dBs, which is equal at 0. It's gonna be equal to 3 in dimensionless. For the case when we have the lambda, the height is equal to 2 over lambda, the directivity is going to be 7.78, so that it's equal to 6. So if we calculate it and make it in dimensional, so 2 lambda, it's going to be around 6 in dimensionless. Okay, just to emphasize and prove the concept that all the equations are working correctly, then we're just gonna look at a problem from the book, which asks you to determine the smallest height that an infinitesimal vertical dipole, electrical dipole of lambda equals to of length of lambda over 15 must be placed above an electric ground plate, so that its pattern has only one null aside from the null towards the vertical, and it occurs at 30-degree angle from the vertical. For that height, find the directivity and radiation resistance. So we could find a solution for this problem using the equations, and we'll come out with a height of 0.288 or lambda from the electric field plot radiation pattern. So if you follow the equations here, you'll end up with a cosine kh cosine theta at theta equals to 30 degrees equal to 0. If you derive cosine this whole equation right here, in order to be to 0 of cosine, we need to have cosine equal this the inside of this equation to be placed equal to 90 degrees. So from that we come out with a height of 0.288 lambda, and using that height we calculate the directivity of that, and we'll end up with 7.1, and using the same height and plugging into the equation for the radiation resistance, we end up with 0.37 ohms. So by using EasyNEC, we'll enter our geometry for lambda for this height. So let me get out of here and bring EasyNEC, and then I'm gonna have this file which I'll be sending you, and I'm gonna look at the wires. So my dipole is gonna have endpoints of 0.288, and add that add the length to the other end of like the size of the lambda over 50. I'm gonna have a 0.308. So if I run this, I'm gonna end up with this kind of plot. So to prove the concept of that, we'll end up with directivity of 7.19, which is equal to from the equation right here, it's gonna be a 7.1 in dBs, which is 5.12 in dimensionless, and demonstrate that this is actually, we're gonna have a null, so we're gonna ignore this null that's being created in at the vertical point, and we're gonna take that null right here. So we starting from here, from this point, that's gonna be right here. The cursor is gonna be, it's at 58, so 58 or 60 divided by minus 90 is gonna give you a null at actually 30 degrees if you start counting from there. Okay, so give it a try, see if you can get the same results, and explore the same thing. You could use the same concept or same idea for the horizontal dipole over a ground plane.